I do have 3 different internal loads here. I have my external load, 3 internal loads or 3 internal torsions, 2 pictures that I was able to get out of this. So it is statically indeterminate in that I can only get 1 equation from each free body diagram, but I have 3 unknowns. So it's not constrained between 2 walls, but I need additional equations to find out what these internal loads are, or these internal torsions are. In the equation step, because we're involving twisting here, I might as well at the front find out what my polar moments of inertia are so I can use them later. For the steel between B and C, we're just looking at the steel. Between B and C, it's hollow, or it's tube-shaped, so we have to use the outside radius to the 4th minus the inside radius to the 4th times pi over 2. So here you should get 1 to the 4th minus 0.5 to the 4th times pi over 2, 1.47 inches to the 4th power. All right, with those out of the way, then we can look at the equilibrium equations. From the first picture, at least in my free body diagrams, I assign x to the right. So if I find the moments around the x-axis in the first picture, I'll have a positive 600 inch-pounds plus TBR plus T steel BC. And the second picture, with the same axes, I get a positive 600 plus a T steel AB. So the second one, I can find the internal torsion in the steel. But the first equation, I will only be able to get a relationship between the torsion in the brass and the torsion in the steel in section BC. So one of them I was able to find. I'll have to use the other one in a substitution later on. How am I going to relate the angles of twist for things I'm looking for and other ways that the geometry of the problem is set up? Yeah. So the angle of twist of that section of the steel is the same as the angle of twist of the brass. That is the BC section. Right, so that's true because they're in parallel, bonded together. What else do I need to know about or what other compatibility equation do I need to solve everything I'm looking for?
The angle of twist at C is equal to the sum of the angles of twist for BC and AB.
Right. Because I'm looking for the total angle of twist at C, I have to relate it back to the wall, which has 0 twisting. So we actually need a second compatibility equation here. It's going to be the angle of twist in the steel from A to B plus, and it doesn't matter which other one I use because I already know they're equal. I'll just say the angle of twist in the steel from B to C. The sum of that is going to be the total twist at point C. So again, we had to see what we're asked to find. This was one of the things we need to find. So certainly it has to appear in equation somewhere. But we also needed that other compatibility to relate the twisting of the brass to the twisting of the steel. And we need that because if we look back here, we don't know them as numbers right now. So we need those extra equations. So we can relate the deformation to the internal loads. Since we already know the internal torque in the steel, or the internal torsion in the steel between A and B, we probably can start there. Will be the easiest. So the angle of twist in the steel from A to B will be the negative 600 times the 36 inches. The modulus was 11.5 times 10 to the 6th psi. And the J was 1.57 inches to the 4th power. All right, so we know that as a number, but now for the other step, we still have to write down the deformation in BC in the steel. We don't know as a number yet what the internal torsion is, but we know that it's 24 inches long. And in this section, the polar moment of inertia was only 1.47 because it was hollow. And in the brass, it'll be T brass times 24 over the shear modulus of the brass was 5.6. And the polar moment of inertia, 0.0982. Right, so how can we solve for the angles of twist we're going to need, because we're going to have to add it to the angle of twist of the steel. So what steps do we need to take to solve this?
When you set those equations equal, find either one or the other in terms of the other one and substitute it back into equation one for that one.
Right, so what we can do is we want to find one in terms of the other. So T brass we can say is negative 600 minus T steel, BC. We can put that into equation 7. And then we know from equation 3, because their angles of twist have to be the same, we can then equate equation 6 and equation 7, solving for that unknown. Negative 581. Yeah. And that is in inch pounds. All right, so using that result, you can go back to equation 1, or the modified version of equation 1, and you can get then the torsion in the brass. Negative 18.9. Depends how you rounded off the intermediary steps here. So about negative 18.9, negative 19, all of that would be acceptable there. So the torsion in the brass, much, much less than the torsion in the steel. Finally, we can go back and we can find what the angle of twist is in the steel, which is also the same as the angle of twist in the brass, times 10 to the negative 4th radians. Yeah, that matches up with what I have. All right, we know the angle of twist of the brass piece. We know the angle of twist of the steel piece between A and B. So the total angle of twist, we should get negative, again with rounding, 2.02 times 10 to the negative 3rd radians. Right, so finally, we need to answer the first question, an interpretation to that with whatever the coordinate system that we established. So with respect to the x-axis, which way should this be twisting? This way, it's fairly obvious since we're only applying one torque here. But with respect to the x-axis, which way should this be twisting? Right, it should be going with the x-axis. But again, we can see from the picture that should be obvious. But from here, we get a negative value for our angle of twist. And I'll represent this in degrees so we have a little bit better interpretation. So 0.116 degrees counterclockwise with respect to x-axis. Our interpretation of our angle of twist is that the angle will be in the opposite direction of t when the angle is positive. It'll be in the same direction as the torque when it's negative. So it's negative, our t is going counterclockwise around x. That means because we have a negative value, the angle of twist is also counterclockwise with respect to the x-axis here. Right? We also want to know in each material, what's the maximum shear stress that it's going to experience. I'll start with the brass because there's only one section of it, so it's just going to be easier. the maximum shear stress in the brass is going to be the torsion in the brass, 18.9. Again, for the shear stress, I don't care about the sign on the torsion. I do care about the sign on the torsion, though, for the angle of twist. But for this, just taking the absolute value is fine. So it's the torsion in the brass times where the maximum shear stress is located. As I said at the beginning of the lecture, or reminded you, the maximum shear stress is going to be at the outside radius. The outside radius of the brass is at 0.5 inches. And the J of the brass was 0.0982. This is in inch pounds. This is in inches. This is in inches to the 4th power. So the maximum shear we have in the brass will be in PSI. It should be at 96 or 96.1 PSI. And since that's the only section of brass we have, it must be the maximum stress in the brass. However, the steel, we have 2 sections of steel, each one with a different internal torsion, but we also have, each one has a different value for J. They both do have the same outside radius, though. So it's not as simple as just seeing which section of steel has the maximum internal torsion, because we're dividing by a different value. So we do need to check both sections. In the AB section, we have an internal torsion of 600 inch-pounds. The steel section in AB, even though it's hollow, the maximum will still occur at its outside radius. For this piece, that's going to be 1 inch. It is 1.57, right? Just looking at it backwards. Right, so the solid section outside radius 1 inch, J of 1.57, internal torque of 600 inch-pounds. So in this section, 382, yes. But we also have that other piece of steel we need to check before we declare this the highest. So the max in section BC has a slightly lower internal torsion, 581. Has the same outside radius, even though, sorry, this section is the hollow one, but outside radius is still 1. But its value of J is also a little bit smaller. So the shear stress will be different here. Here we actually get 395. So even though the internal torsion is lower, because that J also declined, we actually get a higher shear stress in section BC of the steel than we get in AB of the steel. So for each material, then, our maximum in the steel, 395 psi, in the brass, 96 psi.